Hello and welcome to York Universe, the astronomy and astrophysics radio podcast written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'm Senna Withers, I'll be one of your hosts this evening, and I'm joined by Professor Jeremy Webb. We're broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time or on Tuesday morning at 1 a.m. Universal time. We broadcast live on our YouTube page, York U Observatory, and run in concert with our online public viewing program run by our observatory team. To navigate to the live show or to find out more about us, check out our website at yorku.ca/science/observatory and follow the links to the online public viewing to join the live chat on YouTube. For any questions or comments you have on any of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle at URQ Observatory and on Facebook at Allan I. Carswell OBS. All of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. We'll be monitoring the chat room for questions and posting content. The current weather is not that great at the moment, so we won't be doing any live observing with the 1 meter, but we will be showing some archival images, in part taken by the 1 meter telescope on the OPV chat. So Jeremy, how are you?
I'm doing good, Sana. I'm just getting ready for the start of the semester. So lots of busy work to do, but otherwise good. How are you doing?
I'm pretty good. It's really crazy to think that the term is starting next week.
Right?
Yeah, this summer, especially the past month, has really like flown by. It's all of a sudden just been the end of August, and I kind of don't know what happened.
Yeah, I feel the same.
Yeah. But we have a whole lot of interesting stuff to talk about in our show tonight. We have quite a few objects or quite a few things to talk about for our This Week in Space and Astronomy History. And I'm first up tonight with August 25th, 2003, so today exactly, which was the launch of the Spitzer Space Telescope. So we've been talking quite a bit on the show about the James Webb Space Telescope, and I believe we'll be mentioning it a little bit later on as well. But Spitzer Space Telescope was James Webb before it was James Webb. People often refer to as that JWST is the successor to the Hubble Space Telescope, but it's actually the successor to the Spitzer Space Telescope because Spitzer observes the very similar infrared wavelengths to what the James Webb Space Telescope observes. So there's actually a little bit more overlap in the type of stuff that they can do than compared to the Hubble Space Telescope. But anyways, Spitzer was one of NASA's four great observatories. It was the last one of the four to launch, which was basically just a program that NASA had put together where they launched four space-based observatories to essentially just provide high quality coverage of the night sky using multiple different wavelengths. So the Hubble Space Telescope is also one of the great observatories, and these two have since been decommissioned, but there was also the Gamma Ray Telescope. Spitzer has now been decommissioned, and the Chandra X-ray Observatory that is actually still in operation today. So the Great Observatories program and the Spitzer Space Telescope also have just been hugely successful observatories launched by NASA that has really changed our understanding of the universe in a bunch of different ways. Now, before I get into more details on Spitzer, I do want to mention an interesting little piece of information here, which is that the Spitzer Space Telescope is actually named after the astronomer Lyman Spitzer, who was the first person to suggest that people put telescopes in space. Prior to this suggestion by Lyman Spitzer, everybody mainly just did ground-based astronomy, where you just have a telescope, sometimes up on a mountain, to try to get away from the Earth's atmosphere. But Lyman Spitzer was the first person to suggest that it would be really, really great if you could actually take a telescope and put it above the Earth's atmosphere. So you get rid of all of the problems that the Earth's atmosphere causes for telescopes, which include things like, particularly with infrared light, where the sky can actually get very bright in certain wavelengths of infrared light, and it can even block out certain kinds of infrared light from reaching the ground. So if you put a telescope above the Earth's atmosphere, it kind of it just makes your life a lot easier and expands the kind of science that you can do by getting away from the atmosphere. So I thought that was kind of interesting that this telescope is actually named after the person who suggested the whole telescopes in space thing in the first place. So
It kind of means we owe Spitzer thanks for even just things like digital cameras. Right?
yeah,
Like the amount of new technology that had to be developed to like put a telescope in space, take images with a CCD camera and send that data back to Earth. All that technology trickled down to smartphones, digital cameras, things like that. That may not have been developed for a lot longer if we didn't have this push to put telescopes in space.
yeah, exactly. It's always really interesting to think of I know there's a name for these technologies, but I just don't remember what it is. But like like you said, all of this great technology that actually came out of space exploration,
Yeah,
just in general, it's really amazing to think that like you can get so many other practical things out of that, which is pretty awesome.
very
But
cool.
yeah, yeah. So JWST is 6.5 meters in diameter for its primary mirror, but the Spitzer Space Telescope is about 85 centimeter diameter primary mirror. So it was a lot smaller than James Webb, but at the time it was really the only the only infrared space telescope uh, kind of its type. There had been some other infrared space telescopes before Spitzer, but it was basically just the James Webb Space Telescope at the time. So even though it's a lot smaller than James Webb, it was completely revolutionary in a whole bunch of different ways. Now, it launched on August 25th, 2003, from Cape Canaveral, Florida, aboard a Delta II Heavy rocket. And then it spent the next couple of weeks basically just getting commissioned and starting its science operations. This included putting it in the correct orbit, which itself is actually a really interesting orbit. I hadn't actually heard of these Earth trailing orbits before reading about Spitzer. But basically, what the Earth trailing orbit that the Spitzer Space Telescope was put in it's an orbit where it basically follows the Earth or trails the Earth, just like the name suggests. So it orbits the sun, but with a period that is slightly longer than the Earth's. So it is following the Earth essentially in its orbit, but it's moving away from the Earth slowly at a rate of about 1/10 of an astronomical unit per year. And doing so basically just has a couple of big benefits. First of all, it doesn't have to worry so much about the location of the Earth when it's observing. So if you were to put the telescope closer to the Earth, like for example in low Earth orbit, like the Hubble Space Telescope is, you do have the Earth kind of sitting right beside you. So there are a couple more constraints when it comes to where you can point the telescope at a certain time. But for infrared telescopes, the more important thing actually comes from the temperature. So telescopes that look at infrared light have to be very cold to operate properly. Spitzer, in particular, had to be at a temperature of only 5 degrees above absolute zero, which is about minus 268 Celsius. And that's just because when anything, including telescopes or human beings, are warm, we emit our own infrared light. So this poses a lot of problems for infrared telescopes where it can actually start emitting very, very brightly in the infrared. And that basically just kind of obscures a lot of the faint infrared signals that it's looking to detect from objects in space. So in order to get the telescopes to function properly, you have to keep them very cold. And one of the easiest ways to do this is to really just put them in the middle of space, very far away from other things that are hot, like the Earth. So if a infrared telescope were placed closer to the Earth, it would take a lot more effort to keep it cool. In particular, telescopes like this use helium coolant, which can cool the telescope and keep it at the correct temperature, but you kind of burn through a whole lot of this coolant the closer you put the telescope to the Earth. So by putting it far away from the Earth in this interesting Earth trailing orbit, it allowed Spitzer to operate for a lot longer and also made it kind of easier to construct in a couple of ways because you just have this built-in natural sort of cooling system to it because it's far from the Earth. Now, like I said, Spitzer was a really revolutionary space telescope and it transformed astronomy in a whole bunch of different ways. This included studying exoplanets, which it did a whole lot of. It was the first observatory to study patterns on exoplanets. It was also one of the first observatories to find evidence of water on an exoplanet. And it was the telescope that discovered the now famous TRAPPIST-1 system. Now, this system, even today, is still in the news quite regularly because it's still being studied a lot. But it's this system that has 7 Earth-sized exoplanets in orbit around a star. So this is the most Earth-sized exoplanets that have been detected in orbit around a single star. And it also includes 4 of them that are in the habitable zone of that star. So it's a really interesting and exciting system to study if you're doing things like looking for potential Earth-like exoplanets. It was also, so a little bit closer to home, Spitzer was the first telescope to discover a new ring around Saturn, in this case called the Phoebe ring. Um, and it did a whole lot of observing on distant galaxies. For quite a long time until JWST came online, the most distant galaxy ever detected was GNZ11. This was discovered kind of joint between the Hubble Space Telescope and the Spitzer Space Telescope. And yeah, again, it held the record for the most distant galaxy for a very, very long time. Studying it with JWST, this galaxy actually has a whole lot of interesting surprises in it for us. So even today, it's still a very interesting target that's receiving a whole lot of attention and a whole lot of study. And Spitzer was also used to measure the rate at which the universe is expanding by measuring what's known as the Hubble constant. So it did a whole lot of different things in a bunch of different areas of astronomy. It was a really amazing telescope for a very, very long time. Now, Spitzer launched in 2003, and then in 2009, around 6 years after it launched, it ran out of the helium coolant that it needed to stay cool. The mission didn't end in 2009, though. It continued in a modified version of operations called the Warm mission, where it was only observing in the shortest wavelengths of light, which were not as affected by the lack of coolant and by the infrared light that the observatory itself was starting to emit. It continued operating until it was decommissioned in 2020. And it's a little bit sad to think about, but the whole reason that Spitzer was decommissioned was actually JWST. It had received several mission extensions over the years, which were just due to the fact that JWST ended up being delayed. But now with JWST online, NASA just didn't have the money to fund Spitzer as well, since there was quite a bit of overlap in the kind of science that JWST and Spitzer were doing. So it ended up being decommissioned in 2020. But I will note that data from Spitzer, even today, is still very, very useful. I still see it cited in papers, and it's actually being used to make a whole bunch of new discoveries at the moment. So even though Spitzer is not being used anymore, it is still definitely an important space telescope.
Wow. Yeah, I had no idea Spitzer was responsible for so many of those big, like, fundamental discoveries.
Yeah, me neither. I was shocked when I was reading, especially the TRAPPIST-1 discovery, because I remember when this was discovered, it got a whole lot of attention, and I hadn't realized that Spitzer was the one that was responsible for that.
Yeah, and one of the extra interesting things about TRAPPIST-1, even though it's interesting enough, it's the host star is much fainter than the sun, so the habitable zone and all the planets are actually much closer. So the all 7 planets are within like zero point zero 0.05 AU of the star,
Oh
uh,
man.
which is close. Mercury is about zero point 0.5 AU away from the sun, and these ones are all within zero point zero 0.05, so they're all quite close.
Oh
Um,
man.
and I love thinking about like, how would radio communication and space travel evolve if there were 4 worlds all incredibly close to each other that maybe two or more developed intelligent life, where you could, if we had planets that close to Earth, we could have been communicating with them as soon as radio technology developed. And we probably could have traveled to them by the 70s or something like that. So it'd just be really interesting to think about.
Yeah, you could have like your own little bases on multiple different planets if they were
Right?
to each other. Yeah, that would be awesome.
Yeah, or vacation on them if suddenly have a dramatically different climate. But,
That's so
cool.
yeah, yeah.
So yeah, for one of the things I wanted to chat about for the state and astronomy is based on a paper that was published on this day, August 25th, in the year 2000. But it made use of data that was collected earlier that year in January by the space probe Galileo, which was studying the moon Europa. So Europa is a moon of Jupiter. It's a kind of has this icy surface. And what made it really interesting and surprising was that it shows signs of it showed signs of either past or recent geological activity. All right, so if you can think of that and you compare it to our moon, which is geologically quite dead and cold and barren, it's crazy that this moon, way farther away from the sun and smaller in size, is going to be geologically active. And we think this because its surface is quite smooth. Any craters that it likely had after first forming have seemed to have been smoothed out by what appears to be watery or icy outflows that come up from cracks in its surface. Yeah, so people are really interested, so there's this moon going around Jupiter, and it maybe was geologically active in the past, maybe it was still at this time in 2000, but we didn't really know. And so this space probe Galileo, near the beginning of 2000, was traveling out in the outskirts of the solar system and was measuring Europa's magnetic field using its onboard magnetometer. And what it discovered was that Europa had a magnetic pole, a magnetic field, and the pole of that field kept changing every about 5.5 hours or so. And so this paper that came out 25 years ago suggested that this variability, this changing in Europa's magnetic field, was due to Europa having some sort of electrically conductive layer beneath its icy crust. All right, so it didn't have this kind of a solid, boring interior. There was something conductive under there. And so the scenario that they put forth is that, since Europa doesn't have a circular orbit, it's moving around Jupiter and it's experiencing an external magnetic field that's always changing. So Jupiter has a very strong magnetic field, and so if you're passing through that and you're experiencing a varying external magnetic field, if your planet has a conducting interior, it can in turn induce a current or a magnetic field around that body, or in this case, Europa. So the fact that Europa has this magnetic field to begin with suggests it has a conducting interior. And then the models that these scientists came up with to kind of reproduce this changing pole, and by how strong it was and how often it was changing, they suggested that this inner layer was most likely salt water, providing the first direct evidence that Europa has a liquid subsurface ocean today, not just something in the past. So you have this distant icy world that appears to have some subsurface water or salt water, and that really makes it an interesting and enticing object to study if you're looking for life beyond Earth, present day life, because the tidal effects from Jupiter, which can deform and heat Europa's interior in the same way that tidal tides between Moon and the Earth deform each other. These are strong enough forces that could keep the subsurface ocean primarily in liquid form, so it's not completely frozen. And furthermore, models of Europa's interior suggest it has a rocky bottom to it, potentially having hot thermal vents, not unlike the ones we see here on Earth, where we think the first life forms could have come into existence. Uh, Piling onto that and bringing up JWST again, JWST, I think it was a couple years ago now, found evidence of organic molecules on Europa's surface. So you have the ingredients for life and the conditions for life all being present just below Europa's surface. So maybe in time we'll actually be able to tell if life is there. There's some upcoming missions. Clipper and the Juice missions, which between them will have some ice penetrating radar that we can look hopefully a little deeper beneath the surface, and even search for organic molecules. There's some, I don't say controversial, but maybe unconfirmed evidence that there's some geysers from Europa releasing material into space. And so that could even offer a chance of, sweeping up some of that material and analyzing it and looking for signs of life without actually having to disturb Europa's interior. So pretty cool and crazy to think that we're still excited and still studying Europa another 25 years later.
Yeah, the moons of the outer solar system are just so crazy. Like they're in some ways they can actually be a little bit more interesting than just the planets out there. It's kind of crazy to think that it's not just planets that you can find these wacky things on, it's also their moons too.
Right? Yeah, and you think about how, when we're talking about TRAPPIST-1 or whatever, like right now we're really only able to study planets around other systems. But if you start factoring in moons, which I think there's a maybe a small handful of moons around planets, exoplanets that have been discovered, but if you factor in moons as potential places that could host life, it just increases the possibilities significantly.
Yeah. Yeah, I know there was a couple of JWST programs from last year that are now looking for exomoons.
Right?
So I do think that there's other people who have the idea of there's a whole lot of interesting things that are happening on these moons that we should also be looking into. I haven't heard any like results or anything that's come out of that, so I'm not sure exactly what the status is, but it would be really awesome to start hearing about exomoons as well.
Yeah, right. And habitable exomoons and
Yeah.
things like this.
Yeah.
It'll get cool.
Yeah. Like imagine be having habitable life on like a planet that surrounds or on a moon that surrounds a planet like Jupiter or something. That would be really fun.
Right? That'd be cool. And you can just imagine like what the night sky or the daytime sky would look like with some big, Jovian planet with rings and stuff just in the sky or something. That'd just be a cool environment to see and have a civilization in. But then you'd also have to think about how you'd maybe be limited in the astronomy you could do if you're that close to like a giant planet. It's like natural light pollution that you might not be able to get around.
Yeah. Yeah, like I know the moon kind of messes up some observing sometimes because it's just so bright. So you'd ha definitely have more problems on the stargazing front if you had a big Jupiter sitting right next to you.
Yeah. I mean, I guess a lot of Jovian moons are tidally locked the same way our moon is. So they're the same side as always facing them. So you just have to set all your observatories up on the permanent night side or something like
Yeah.
that.
Yeah, it's definitely a cool concept to think about.
For sure.
But speaking of planets, my next topic for this week in history is actually from yesterday in 2006, August 24th, which was when the International Astronomical Union formally defined a planet for the first time, which also included demoting Pluto and a couple of other smaller shakeups that ended up coming from this formal definition. So one of the things that I hadn't realized is that the IAU actually didn't have a like solid definition for what a planet was before 2006. So things were a little bit sort of uncertain at the time, and different objects in our solar system could be considered planets sometimes by different people in different circumstances. So one of the things I did when I was reading about this is went back to the how we originally defined planets, and this definition comes from very, very early astronomy with civilizations like the Greeks, for example, who defined planets based off of their motion in the sky. So what they noticed was that all of the stars in the sky moved from east to west in pretty much the same rate. But you did have a handful of very bright objects like Mercury, Venus, Mars, Jupiter, and Saturn that were moving through the sky at a different rate. And Mercury and Venus in particular would sometimes even have retrograde motion. So they called these objects the Wanderers, which is actually where we get our word for planet from today. For quite a long time, there were only those five planets known in our solar system. Earth was eventually added to the list of planets when the Copernican model was accepted, where you have all of these different planets orbiting the sun at the center of our solar system. And then those definitions changed again when Uranus was discovered in 1781, when that was added to the list. And then again in 1864, when Neptune was discovered and added to the list of planets. Now, people started to run into problems when astronomers started discovering a whole lot of other things in our solar system, which may or may not be considered planets. This includes the asteroid or the massive asteroid Ceres, which we actually were able to, I think we observed Ceres a couple of months ago. It was pretty bright and an interesting thing to observe. But astronomers were discovering things like Ceres that were in between the orbits of Mars and Jupiter, and also objects further out in our solar system system beyond the orbit of Neptune, which included Pluto, which was discovered in 1930. Now, Pluto's discovery was kind of interesting because when it was first discovered, there had been some discussion about a missing planet X, which I think there is still a little bit of discussion around an extra planet in our solar system now. But for a time, astronomers believed that Pluto was a lot more massive than it actually was. So it was believed to be Planet X for a period of time. Eventually, astronomers also discovered its moon, Charon, and discovered that they had wildly overestimated the mass of Pluto, and it was a lot less massive than they originally thought it was, which helped to kind of spark a little bit of debate around exactly what objects in our solar system should be considered planets, what should be considered asteroids, or what should be considered what people had called for a long time minor planets in our solar system. Now, this debate continued to kind of accelerate and heat up a bit in the 2000s when astronomers started to discover just tons of objects that looked a lot like Pluto. They had similar orbits, similar masses to Pluto, and it had started to become clear that astronomers were going to be eventually discovering a lot more objects like that in our outer solar system. So they kind of came to a conclusion where they either needed to have a status that really clearly defined what a planet was. That could include Pluto, but by including Pluto, you would also be including hundreds, potentially even thousands of other objects in our solar system as planets. Or they needed to come up with a definition that excluded Pluto as a planet. So we would end up with the 8 planets in the solar system, and Pluto and anything that looked like Pluto would be excluded. So this debate eventually sort of led to the creation of a committee by the IAU in 2005, which were tasked with coming up with an actual formal definition of what a planet was. They had a couple of different ideas of how they were going to define what a planet is, including one proposal, which I believe was the first one that they presented to the IAU committee, which would have included Pluto as a planet, as well as Ceres and Eris, and actually would have created a special class of planet for Pluto where it was considered to be a double planet, since Pluto and its moon Charon were kind of similar in size and were orbiting each other. So it would have kind of created this really complicated definition of what a planet was and created that new class of a double planet to keep Pluto included in a planet. So, unsurprisingly, this was kind of an unpopular idea, I think, because it's a little complicated. When I was reading the definition, it definitely seemed to be a little bit complicated, but they ended up making a few important changes to this definition of a planet, which ultimately led to the current IAU definition of a planet. So, I'm going to read pretty much word for word what the IAU definition of a planet was, which has 3 conditions at the moment. So, first of all, it has to be in orbit around the sun. Second of all, it has to have a sufficient mass for its self-gravity to make it into a nearly round shape. And 3, it has to clear the neighborhood around its orbit. Now, in this definition, it excluded Pluto as a planet just because of the third definition, where it has to clear the neighborhood around its orbit. Pluto crosses into the orbit of Neptune, so it's not the most massive thing in its orbit around the sun, so it's not a planet. It also meant that other things like Ceres and Eris were also not defined as planets. Now, as a part of creating this definition of a planet, they also decided to do away with the name of minor planet and use the definition instead dwarf planet, which has the first same 2 conditions. So it has to orbit the sun. It also has to be nearly round, but has a different third condition, which is that it has not cleared the neighborhood around its orbit, and has a fourth condition that it is not a satellite of some other body in the solar system. So that classifies Pluto and other objects in our solar system as dwarf planets, but then the planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune as actual planets in our solar system. So that decision was made in 2006 on August 24th, so yesterday. And it's kind of an interesting thing to read about because every single time I see anything related to the IAU definition, it always really focuses on Pluto and like how unfair everybody's being towards Pluto. But it really seemed at the time like it was kind of a long time coming, where it was actually causing some problems for astronomers of, what exactly do you consider a planet? What's considered an asteroid or a minor planet or things like that.
Yeah, so this was interesting when you brought this up. I'd never looked up like the formal definition online. I think it like from the IAU, and I had never seen this fourth point is not a satellite. I thought if it's in orbit around the sun was by definition not a satellite, but I'm guessing they threw that in there for a specific reason.
Yeah, I'm not really sure. I thought it was kind of odd when I saw that because yeah, if it's a satellite by definition, it's not orbiting the sun. Um,
Yeah,
but
there must have been something in particular they were thinking about that to kind of throw in that extra term. But yeah, so when I was a kid, I grew up with Pluto being a planet. So for whatever reason, I have this sentimental attachment to Pluto too. But
yeah,
I'm sure had like, all these other things been discovered too when I was a kid, or if Pluto was already a dwarf planet before I really started thinking or caring about these things, I probably wouldn't have noticed. But for whatever reason, it makes me sad.
yeah. Yeah, I don't know. I know some people who have very strong opinions on Pluto's planetary status.
Mm,
So it's always kind of a fun debate, but a lot of the time it's kind of interesting because like I said, there's so much attention that gets focused on Pluto for a lot of this, but it really seems like there were a whole lot of other um, astronomical bodies and things that had been discovered in our solar system that led to this whole argument. So it wasn't just Pluto that was affected. And as a result of this decision, there were actually formal definitions for other objects in our solar system that were put in place as a consequence of it. So, like
mm.
trans-Neptunian objects, for example, they have like their own definition, and part of that decision to make that came out of this whole debate of what exactly is a planet. So it kind of seems like in 2006, the IAU decided to actually establish rules. Um,
Yeah,
there were some consequences that kind of came out of that.
right. Yeah.
Yeah,
And
but
I feel like so if if you magically had all the knowledge or information in the world, or you could time travel and watch our solar system evolve over time, a proper definition would probably just be how it formed and maybe a little bit more about, how its interior developed. Did it get massive enough to differentiate? Does it have, all the dense stuff at the center? Was it ever geologically active? And then, yeah, what was its formation channel? That'd be probably a proper definition of a planet, but we're kind of stuck looking at the solar system as it is today.
yeah, that's a cool thing to think of also, because if you're looking into defining what a planet is, like that, I guess might change over time depending on what state the solar system is. So, yeah, that sounds like a better definition of a planet.
Right? Yeah, if we could somehow, even Pluto has since surprised us with the was it Event Horizons that did the flyby of Pluto however many years ago?
Yeah, New
Um,
Horizons.
New Horizons, yeah, yeah, New Horizons. We kind of thought Pluto was this boring, sphere of ice out there, but then after this flyby event, we took some pictures. It actually looks like Pluto was maybe geologically active in the past, and it has a lot more complicated history. So if you think about a definition in terms of, gathering up enough planetesimals and having a differentiated interior and having a period of geological activity. I don't know. Maybe you would call it a planet that has since cooled or something like that,
Yeah.
just based on its history. But we're probably a long way away from being able to confirm any of those kind of things.
Yeah, with all of the attention and controversy that came along with this planet definition, I doubt the IAU is looking to redefine things anytime soon. Yeah.
It's kind of funny they spent the time on doing it. There's so many horribly named things in astronomy, like just based historically named things that have stuck around. The names have stuck around. So like I feel like you'd either have to go through and properly redefine a whole bunch of stuff or
Yeah.
just accept that the historical naming is stuck the way it is, and yes, we're going to find new observations and new information, but you just keep it.
Yeah. I mean, astronomy has done that with things like units, so why don't you just do that with the names? Uh,
Right? Yeah, yeah. There's yeah, it's funny. My favorite is like was it planetary nebulae?
oh
Because
my,
for a
yeah.
long time when they observed however many hundreds or decades or a few hundred years ago that we thought they were like planets or little clouds that would turn into planets, but now we've learned that are there because of the death of a star, but we still call them planetary nebulae, even though
Yeah.
they've nothing to do with planets.
Yeah, that's always a fun thing to explain to people. Like, we're looking at the Ring Nebula, which is known as a planetary nebula, but it has nothing to do with planets.
Right? Yeah. Yeah. Even like dark matter and dark energy, like it implies they're like related somehow.
Mhm.
Um, but really the word dark just means we can't see it. They're not connected in any way.
Yeah, yeah.
Um,
But you have another really interesting This Week in History item also from our solar system.
yeah, we're kind of bringing things we're kind of wrapping everything. We talked about moons, we talked about planets, touched on dwarf planets and asteroids. And then one thing I wanted to talk about going way back to 1835 is Halley's Comet. I mean, Halley's or Halley's, I'm not sure. People say both. I'm going to go with Halley's, but people can correct me if I'm wrong. So in August of 1835, there was a passing or a return, if you will, of Halley's Comet. This is a comet that travels around the sun between 72 and 80 years at a time. It varies with each orbit. And it's exciting comet because you can see it with your eye when it passes close to Earth. And so it has a pretty big orbit. It has an 80-year period. It means it's going all the way out to kind of between Neptune and Pluto. And then when it travels into the inner regions of our solar system, it's kind of reaching between Mercury and Venus before turning around and heading back out again. Now, sightings of Halley's Comet actually date back to about 240 BC. We found evidence in different from different civilizations and different cultures of sightings of this comet dating back that long. But it really wasn't until 1705 that Halley used observations of the comet that he had taken, I guess, almost 30 years before that, 1682. He used those observations, Newton's recently published of law of gravitation, and realized that this was the same comet that had just kept coming back every 70 to 80 years or so. And so all these previous sightings were the exact same thing. And then he then predicted it would return in 1758, which was interesting for two reasons. One, it's just it's a pretty big prediction to be able to make with our understanding of physics and astronomy and observations at the time. Like I said, Newton's law of gravitation had maybe just been published around the same time. And it's also interesting that he made this prediction and he unfortunately didn't live to see it. Uh, and so you can imagine like, oh, I've made this big prediction and I think I understand everything, but I'm not going to be alive in 70 to 80 years from now, so I'm not really sure how it's going to turn out. Um, but sure enough, it did appear again in our night sky in 1758. So that's when it was named after him. And it's also a really interesting example of time scales in astronomy, or even distance scales. We're looking at things that are far away, things that happened in the past, and we're trying to study and understand them. But we're nowhere near being able to visit them and actually maybe confirm some of our theories. So we just make as many observations as we can, make predictions, and we might not know for some time if any of our predictions are true. What also made this 1835 passing interesting was that these updated measurements, we got more accurate estimates of its position and its motion, and more accurately traced its orbit, and is able to confirm a few more passings of the comet in the 1400s and 1300s. And really this big step that Haley did of connecting the dots between Newton's laws to predict past observations and past civilizations, it turns out nearly one eighth of the cometary sightings in human beings past were actually just Halley's Comet coming back and forth, back and back again every 70 and 80 years. And then one final interesting tidbit, again relating to August 1835, when this passage of Halley's Comet that I'm talking about happened. This is also when Mark Twain was born. Uh, and he once famously joked that he arrived with Halley's Comet when he was born, and he planned to leave with it too. I think the exact quote is, "I came in with Halley's Comet. It is coming again next year. The Almighty has said, no doubt. Now there are these two unaccountable freaks. They came in together, and they must go together." And coincidentally or not, Twain died in 1910, the day after Halley's Comet made its return. So kind
Oh,
of interesting, kind of weird, but there you
yeah,
go.
that is interesting and weird. Yeah, exactly. Yeah, it's also
Yeah, just
sorry, go ahead.
no, just no. Go ahead. I was just
Yeah.
gonna say,
Yeah, I was just gonna say that's crazy that like an eighth of the comet sightings are just Halley's Comet.
right? Yeah. That was really surprising when I read that.
Yeah. Comets are really really amazing things to observe. I remember one from I don't remember the name, but it was during COVID. I got a couple pictures of the long comet tail. I just missed being able to see it by the naked eye because I live in very light polluted skies.
Okay.
It would be really cool to actually see a comet with the naked eye. They really seem like amazing objects.
Yeah, and I love the ones like Haley that you can see with your naked eye. It's really interesting then when you're doing like historical or cultural astronomy, and you can see that all these different civilizations that actually took note and actually wrote down or charted down the appearance of this object in the sky. And you could even imagine, um, we know it's a comet when it shows up, but 200 BC or whatever I said, 240 BC, this real bright thing with a long tail shows up in the sky, and you don't have, our understanding of astronomy at that time was limited. That'd be a pretty, I don't know, startling, weird, terrifying thing. I don't know.
Oh yeah. Yeah, I think there is some mythology also around what exactly comets are of ancient civilizations observing them and just thinking like it was I think in some cultures it was treated as kind of a bad omen where it was
Yeah,
a sign of like bad things to come. But today we look forward to comets because they're really
right.
cool.
Yeah. I remember there's a thing about Shakespeare and astronomy too, where he always uses comets as bad omens in his work as well.
Yeah. Yeah, so definitely interesting how times change with more information. Uh
Right? Yeah.
But we are at around our halfway point for tonight. So for anybody who's just tuning in, you're listening to York Universe, broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. If you'd like to join our OPV chat for some archival imaging or to ask questions, please head over to our website, yorku.ca/science/observatory, and follow the links. Tonight, you've been listening to myself, Senna Withers, and Professor Jeremy Webb. We've currently been discussing some astronomy history, including Halley's Comet and Pluto, and a couple of other kind of solar system related things. We also have a couple of interesting news items to get to. But a couple of quick reminders before we do that. The observatory is actually open on this Wednesday for an arboretum tour. So we're not at the actual observatory itself. We're at our location on top of the arboretum parking garage with our 40 centimeter telescope and a couple of other smaller telescopes. So if you'd like to come around and do some stargazing with us, please join us there. We do just ask that people get tickets ahead of time. They are free, but please just get them from our website, yorku.ca/science/observatory. We also have a really exciting event coming up on Friday the 29th, which is our monthly Teletube broadcast. This week is going to be featuring the observatory's own Nakul Sathuram, who's going to be talking about his research on lava planets that he's been doing recently. So that should be a really interesting Teletube, and a couple of great events coming up this week for anybody looking to visit the observatory. Now, in terms of the space news that we have, we've got two things coming up. I'm up first with a really cool new discovery on fast radio bursts, or FRBs. Now, FRBs have been kind of in the news a lot recently, because they're these kind of crazy, weird events that people don't fully understand at the moment. So they're exactly what their name sounds like, where it's basically just this really, really short-lived burst of radio waves that comes somewhere in space. Most of the time, kind of coming from other galaxies. Potentially, sometimes these radio bursts can come from billions and billions of light years away. When I say they're short bursts of radio waves, I mean the bursts tend to last things like milliseconds. A very small number of them can repeat, but most of them are just sort of one-off events. So these are really interesting events, partly just because they're so energetic. The article that I read on this actually stated that these one bursts that last like milliseconds or as short as milliseconds can emit as much energy as the sun does in its entire lifetime. So very energetic, very interesting events. And so far, the kind of best reasoning or sort of on what causes them are actually their magnetars. So these are just neutron stars, which are the remnants of massive dead stars, which can have these really crazy strong magnetic fields, and that there's something happening with these magnetars that are launching these fast radio bursts. Now, one of the big problems of figuring out what these fast radio bursts are actually getting follow-up observations on them. So while a radio telescope can pick up the initial fast radio bursts, it can be really hard for these radio telescopes to kind of triangulate precisely where these bursts are coming from, which means that it's a lot harder for other telescopes like the James Webb Space Telescope, for example, to actually be able to triangulate and, pick up on the signals coming from that fast radio burst. Now, this changed recently because of the Canadian radio telescope CHIME. CHIME has been doing a whole bunch of really cool stuff. This includes mapping neutral hydrogen in our galaxy. But one of the other modes of operation that Chime has is an FRB mode, where it can actually detect a bunch of fast radio bursts, and it's been hugely successful at doing this. Now, recently, Chime was upgraded with a couple what are called outrigger stations, where they just added more versions of Chime essentially to different parts of North America, which include going all the way from Penticton, BC, which is where the original Chime array is and Chime Telescope is, all the way out to California. And one of the benefits of adding these outrigger arrays is that it now allows Chime to actually pinpoint very, very precisely where these fast radio bursts are coming from. And that's exactly what it did recently. So back in 2025 in March, Chime detected an FRB which is officially called FRB 2025-0316A, which is basically just after the date that the FRB was detected. But astronomers are calling it the radio brightest flash of all time, or RB float for short. I'm not sure if that's the pronunciation they were going for, but that's the kind of how I read it when I first saw it. So this is just yet another example of astronomers giving things kind of bad names. RB float is a bit of a mouthful, and the official name isn't that much better either. Um, but at the time, this is the brightest FRB that has ever been detected. And because of Chime's upgrades with the outrigger stations, it was able to track down the very, very precise location of this FRB to the edge of a galaxy called NGC 4141 in one of the spiral arms. So this was kind of a first. FRB arrays like Chime have never actually been able to precisely track down the location of an FRB until Chime did this with the outrigger stations. So that in and of itself is a really great discovery. And because of that, the Chime team who discovered this FRB were able to get follow-up observations from JWST and actually pinpointed a very, very faint near infrared source that existed right beside the location of this very bright FRB that they've dubbed NIR1. Now, there's a little bit of debate or an uncertainty about what exactly is going on with the FRB and NIR1, because NIR1 itself is actually a red giant star, but FRBs cannot come from red giant stars. FRBs are just way too energetic for that, so it's not really possible for stars like that to produce FRBs. So what the team has been kind of theorizing at the moment is that there is a neutron star that is right beside this red giant star, and it could be pulling material off of the red giant star and in turn launching an FRB. So this is exactly the kind of science that you wanted to be doing with these outrigger stations on Chime, where you can actually start to track down the locations of the FRBs, and because you get a very accurate location of where they are, you can then figure out, what's going on with the FRB and what's happening in the environment of the FRB. So, very interesting discovery. Still, definitely a lot to be learned about this FRB, but hopefully more work like this in the future will help kind of narrow down exactly what is launching FRBs and what their nature is.
Yeah, they're really crazy, interesting, energetic objects. And I love that you mentioned Chime. Chime's a great example of Canadian astronomy and collaboration at play. It's like you said, it's the first one's based out west, and it's I think it's co-led by UBC, McGill, uh, U of T, University of Toronto, and it has a lot of Canadian insert funding as
Yeah,
well. And then there's various other North American institutes that are involved. But yeah, definitely a Canadian-led instrument, which is pretty cool.
yeah. We also have a professor at York now, Paul Scholes, who works with Chime FRB. So
Right.
York as well. Yeah.
Yeah, it's
But
absolutely very, very cool.
yeah, but in our last few minutes for tonight's broadcast, you've got an interesting discovery about our solar system.
I do, yeah. So yeah, if anyone listening may or may not have heard it in the news recently, but there was a lot of chatter about a new moon being discovered around Uranus, which is cool. I love stuff like this because we have, as we've been talking about, we have these telescopes, supercomputers helping us observe and understand things that are really far away. Talked about Spitzer's finding some of the oldest, most distant galaxies at the time. But there's still a lot to learn and discover about our own backyard. And so finding a moon around a planet in our solar system is pretty cool. But it's perhaps worth highlighting here what we mean by a moon for Uranus. And it's actually kind of relevant given our discussion of Pluto earlier about what classifies as a planet. Um, I don't think the IAU has gone to the extent they did for a planet to define a moon. Um, but I think you can loosely think of a moon as roughly anything that orbits a planet and is relatively alone in its orbit. So it kind of has that cleared its orbit property planets have. But they don't have to be spherical or anything like that. So this newly discovered moon is actually quite tiny, only about 10 kilometers in diameter. So very tiny compared to our moon, for instance. Plus, Jupiter and Saturn have hundreds of moons, if you count the kind of things that are only tens of kilometers or even just a few kilometers in diameter. Although the really tiny things that haven't cleared their orbits, they kind of get sometimes flagged as moonlets or proto-moons. Um, but so far, this 10-kilometer diameter object around Uranus is being called a moon. Um, and it's a pretty active field in astronomy, searching for moons around our own outer planets, because it really helps us understand our solar system's history, especially if you can figure out, is this moon something that's left over from when Uranus first formed? Is it something that was gravitationally captured by Uranus? Or is it something that broke up completely while interacting or colliding with Uranus? And figuring out its orbit and, if possible, its chemical composition can tell us about its history. So this particular moon, which has some sort of alphanumerical name, like S 2025 U1 or something like that, it has a pretty close to circular orbit in the inner, very close to Uranus. And it orbits in Uranus's equatorial plane, so kind of just around in the same level or orbiting around the equator essentially, as opposed to some funky inclination, which strongly suggests it formed there. Its orbit hasn't been altered since formation. Um, and adding to this kind of interesting discovery is that Uranus has the most small moons that have circular orbits close in its equatorial plane, close to it, suggesting that its formation history was perhaps a little different than the other Jovian moons, or for some reason, those kind of moons of Jupiter and Saturn, can't survive long in that region. Or maybe were pulled into Jupiter and Saturn when they first formed. So, still asks or leads to a lot more questions, but the more data, the better. And now I'm especially excited though to see if this moon gets a more exciting name, something better than S 2025 U1. because the moons of Uranus fa are famously named after either Shakespeare characters or characters from an Alexander Pope poem. And the reason this happened was the fact that when Uranus was first discovered, first observed, the discoverer, Sir Herschel, wanted to name it after King George, the British monarch at the time, and he wanted to honor his British heritage. But this made all the other astronomers at the time pretty unhappy. It's very clear naming history of planets based after Roman and Greek mythology. So there was just no way anyone was going to allow him to name Uranus after King George. So he did give in, and obviously Uranus was named Uranus. But he also found not too long after that the first two moons of Uranus. So he said, you know what, I'm going to name these in a way that honors my British heritage. So he named them after Shakespeare characters. So it's kind of cool when you're going through the objects of the solar system and you see these moons of Uranus and they're named, like Juliet or Puck or Titania and things like this. They're all, familiar Shakespeare characters, which adds a little bit of fun history and fun literature connection to astrophysics.
Yeah, the IAU definitely has strict naming conventions in place for for new moons. Um,
Right.
yeah, you mentioned the what was it, the moonlet?
Yeah.
Yeah, I've never heard that terminology before.
Yeah, so I've heard people call moonlets for these tiny little moons that exist in planetary rings. So you'll have, Saturn's rings, but then within the rings, there's what they call a moonlet that has pretty much created a gap in the ring, except for where it is on its orbit. So that's where I first came across the term. That it's in the rings, but it's still cleared its orbit, but it's still kind of small. So I've heard things called those kind of objects called moonlets.
Yeah. So it's kind of I think the Cassini division on Saturn is kind of caused by one of those little moonlets, right?
Yeah, yeah, things like that. Yeah.
Yeah, that's pretty cool. Yeah, again, like moons on the outer solar system are just so cool.
Yeah, yeah, and the fact that people are like finding things like just a few kilometers in size, and that's telling us about how they formed is pretty cool.
Oh yeah. Yeah, we just
Yeah,
need to send missions back to Uranus and Neptune, honestly. Like I know they're
right. It's been a while.
yeah. Yeah, you mentioned the ones coming up to Europa, but like I think the only time that there has been spacecraft that f did flybys of Uranus and Neptune was like Voyager 2, right?
Yeah, yeah. Voyager 2 did the flybys, and then yeah, I don't know, has anything orbited
I don't think
Neptune?
there's
I
been
don't
any
think
like
so.
dedicated orbiters for Uranus and Neptune. There's
Yeah,
been ones at Jupiter and Saturn and pretty much everywhere else, but just not Uranus and Neptune.
yeah, yeah, exactly.
Yeah, and if
Did
you think
yeah, did New Horizons? I don't know, because I don't think
I
New
don't think
Horizons
so.
was like it didn't pass those planets when it passed that distance from the sun, so it just didn't work out.
Uh,
Yeah, no, they need to do that.
yeah. Yeah, because I mean if you think about like kind of Cassini and it's Cassini and Juno kind of that I'm thinking about. If you think about all of the like really awesome things that those two spacecraft discovered that you had to be like in orbit around these planets to discover, it's kind of crazy that nobody has gone back out to Uranus and Neptune.
Yeah, yeah, it really is. So I very quickly Googled this because I know we're almost out of time. Apparently there's no planned missions to Neptune. There's a couple conceptual ones, but nothing official. But there is a Uranus orbiter and probe that maybe it's been flagged as a mission priority by NASA, but might not get launched until the 2030s.
Okay. I mean, it is 2025, so 2030s is, I guess, a kind of reasonable deadline for when that would launch, given how long it takes to kind of build these space probes and everything. But,
Yeah, and then you still got to wait another while to get there. So I think this one random article I'm reading says that if it got launched in 2031 using a Falcon Heavy rocket with a gravity assist from Jupiter, it still wouldn't get to Uranus till 2044.
oh man, that's too far away.
So yeah, even if it gets launched in 6 years, we still got another what does that end up being? A good 15 years, 13 years later till it gets there.
Yeah, maybe that's why space agencies are so reluctant to launch these probes, is just because it takes so crazy long. Uh,
Right? Yeah, you can get a maybe more immediate bang for a buck if you want to either study Mars or build a telescope.
yeah,
You have to have a pretty strong science case to go there.
yeah, yeah. But yeah, poor Uranus and Neptune. So all of the things in the outer solar system are kind of neglected, it looks like.
They got all their moons to keep them company though, apparently.
Yeah. Pluto had a visit, and I guess that's all anybody wants to do for the outer
Yeah,
solar.
that's all anyone wants to know about Pluto.
Yeah. Yeah, but the New Horizons mission was really amazing. This is definitely not scientific or anything, but I can't get over how cute it is that Pluto has a little heart on it. Like
Right.
it's the sweetest thing. Like we demote Pluto and it's saying I still love you. It's so
Yeah. Still all about the love, everybody.
yeah. Yeah, well, we are pretty much at the end of the hour. So for everyone who's been listening, you've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Professor Jeremy Webb and myself, Senna Withers. You can always connect with us on Instagram at the handle at URQ Observatory and on Facebook at Allan I Carswell Obs. And check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in to York Universe. Clear skies and have a good night.
Thanks, everyone.